Hi, and welcome to Material Physics 5. Today we're going to be finishing off some of the ideas we've been looking at angular momentum, and also looking at rotational energy, which is the angular equivalent of kinetic energy. How much energy something has because it is spinning, as opposed to how much energy something has because it is moving. So, in our standard momentum model, we know that kinetic energy is equal to half times the mass times velocity squared. Easy. So let's think about angular momentum, our rotational energy. So remember, this is how much energy something has because it is rotating. And if something is rotating at a constant speed, that energy will be constant. So the Earth, if you want to slow down the Earth so it wasn't rotating anymore, you'd need to put so many joules of energy to resist the energy it already has because it's rotating on its axis. That's going to equal half times, well, instead of mass, we're going to be using the moment of inertia. And instead of velocity, we're going to be using angular velocity squared, or omega squared. So exactly the same thing you'd expect. The more inertia it has, remember this is similar to mass, it's how much it resists being turned, and the faster it's spinning, the more rotational energy it has. Simple. So we've got a couple of very slick things we can just put in here. So instead of power being force times velocity, power is going to equal torque, because remember, torque is our turning force times angular velocity again, how fast it's spinning. So that's nice. Work done, instead of being force times distance, is going to equal torque times, can you guess what we're going to use instead of distance? Just think for a moment. It'll be the angle it moves through. So it's actually torque times angle swept out as opposed to distance, because instead of moving in a straight line, we're spinning round and round. This means you can also write work done if you're being a little bit more mathematical, and this is how you'll see it a lot more at university. So it's going to be much more describing things in terms of integrals. It'll be the integral between the two angles of your torque with respect to the angle. So this and this are two different ways of saying the same thing, but you're going to be doing it a lot more in this notation. Okay. Let's just have a little think about torque. So torque is a turning effect. So whenever we've got a lever and we're turning something, that force is our torque. So in a very simple basic level, if we know the force we are applying, and we know the distance, which is generally referred to as r in rotational physics, from the fulcrum, we will know the turning effect. And obviously as we increase the distance or increase the force, we'll get a bigger turning effect. That's just standard lever stuff. But crucially, all this only works if these are at 90 degrees to each other. So if the distance from the fulcrum has to be at 90 degrees, perpendicular distance, and the force has to be at 90 degrees to the distance to get our moment force. But when you move up to university physics, it's not going to be simplified like that. And what they're going to do is they're going to use a lot of the maths that you've studied and bring that more and more into the physics and get more mathematical. So we could say our torque is equal to the force times the difference times sine theta, where theta is the angle between the actual force and where we're going from here. So we could do it that way, but we can also just do it as the cross product of the vector of the force and the distance, and that's where your cross products come in. This is especially useful in multiple dimensions because we can replace these scalars with three-dimensional vectors, and then we can do the cross product there. So that's how we can work out torque using cross products, and that will also give us three-dimensional torque. Okay, so these are some more things that we should know about momentum and angular momentum. Now, I'm going to show you some neat things this allows you to do. The first one relies on rotational energy. So while you are standing on the Earth, you have quite a lot of rotational energy inside you. And in fact, we can use this when we're launching spaceships into space. Because they're already on top of a spinning body, if you launch them in the same way the body is spinning, they'll get a big slingshot effect because they're already going so quickly. So here's the Earth. The Europeans actually have a space station in French Guinea, 5 miles north of the equator, So here's your equator, because if you think about it, at this point it's going to be spinning as fast as possible. And if you launch off into space here, you get an additional 1,000 miles per hour just for free. Now, the Kennedy Space Center is quite a long way north of the equator. It's at a latitude of 28 degrees. And if you launch from here, you only get 900 miles per hour of speed just from your rotational energy from being on the Earth. So by being closer to the equator, you get a faster slingshot off into space because you've got more rotational energy, which is pretty cool. Another use of rotational energy is in something called a flywheel. Now you might have seen a flywheel. If you've ever seen one of those big machines, it's just a massive weighted wheel that's spinning round and round. Now a flywheel is really neat because it's basically a battery. By putting lots and lots of energy into spinning the flywheel, you can then keep the energy there or just store it as rotational energy. It'll be losing a very small amount to friction in the bearings, but as long as you keep that really low, that's a really sensible place to store lots and lots of energy. And if you're making a machine that's a little bit naff, and the force going in is, you know, a little bit inconsistent because maybe your pistons aren't always firing and what have you, if you use them to accelerate the flywheel and then you draw the energy off the flywheel, you can get a nice consistent source of energy off the flywheel, even if the forces going in are a bit all over the place. And this allows you to create much, much more level forms of energy by using the flywheel as a place to temporarily store the energy. Flywheels have been around for ages. Ibn Bassal, who was an Islamic scientist working in Spain at around 1000-ish, so about 1,000 years ago, he wrote a lot about flywheels and in fact made quite a few machines with them, which was interesting because he's mainly known for his work on gardens. He was a fabulous gardener and made beautiful gardens all throughout Seville. But he also just did a sideline in flywheels. If you go to the Museum of Science and Industry, you'll see most of the machines there actually use a flywheel as a battery, taking the energy out of those steam things with all their turbines, which can misfire and be a bit faffy, storing it in the flywheel, and then you draw energy off that. You can also use a flywheel to power multiple smaller machines off just one bigger engine. So by storing the rotational energy, you can use it as this really cool kind of mechanical battery. Okay, great. There's a question underneath. I'll see you later in the week.